Our robot Qbot is designed for collecting power cells from the floor and shooting them to inner and outer ports. Qbot can climb and move forward autonomously.
We use box profile and sigma profile to produce most mechanical systems. We prefer sigma when we need robustness and box profile when we need lightness. Parts are joined by using laser cut aluminum L parts.
We are using 6-wheel drop center drivetrain and controlling it by differential drive mode.
As Qubits related to our team philosophy, we designed this system to perform as both a shooter and a power cell collecting mechanism. This system acts as a shooter while it's pointed upwards and acts as an intake while it's pointed downwards. It is designed for saving space and weight. There is a pneumatic piston for changing the stages between shooter and funnel modes.
The intake system is collapsed by default as it extends beyond the size limits. It extends by a piston that is connected to a solenoid valve.
We redesigned our shooter mechanism for the 2021 challenge. It is more rigid now. The hub you can see at the second picture is lathe. We keep in touch with industrial area, we design and learn how to produce parts.
This funnel is used for transferring the power cells to storage or reverse. The pulley system is a solution to provide the power we need.
We use a bell system on our storage mechanism for storing power cells one by one and avoid them getting stuck. We formerly made our storage compartment out of plexiglass. However, we ditched this idea because we found out that power cells can't slide the way we want them to on plexiglass. This created the problem of power cells being stuck in the system. We eventually settled on aluminum sheets, which worked like we wanted. And to add lightness, we cut off triangular shapes as that was the way to go if we didn't want to sacrifice rigidness.
We have chosen to do the climbing with the piston because when the robot climbs with the rope, it goes back down when the power is cut off. There are two 50 to 600 pistons which we place both sides of the robot and we can carry out our climbing task thanks to them. We combined the two pistons with the sigma profile above the robot. We added a hook in the middle of the sigma profile. When we added the hook, the robot became too tall, so we added the hook in a horizontal shape and put a bow between the hook and the piston. The point of that was when we aerate the pistons go up and the hook goes up as well. Thanks to that, we completed the climbing task with success.
Bahçeşehir'in kancası şu anda havada, henüz kalkan jeneratörüne yaklaşamadılar. Derken kırmızı ittifakta iki droid, Robot ve Qubit Robotics droidleriyle şu anda havada asılı kalmayı başardı. Mavi ittifaktan buna henüz cevap gelmedi. Son 3, 2, 1.
Due to our school system, learning basic Python is mandatory for high school students, so we are using the Python programming language in our robots. We see this as an opportunity to implement FRC into our education. We perceive the robot environment with image processing technology using a Raspberry Pi 3 as a coprocessor. We think this will facilitate our success in autonomous activities. We have two functions running the same motors, acquiring the power cell and shooting the power cell. The robot constantly checks if there is a power cell or not in the storage through the color sensor to prevent the motors to run in vain or getting our storage limits. Both functions run all the motors and solenoids except the climbing solenoid. The only difference between them is the direction of the motors and the solenoids. We can say that the two functions are the complete opposite from each other. As you may have noticed, the same engines are running in these two processes. This makes the robot more functional as it saves both space and energy in the robots. Apart from our main functions, we also have functions to control all engines and pistons manually. We added this to be able to control the robot in case of any ball jamming or security risk.
The compressed air in the compressor is stored in the pneumatic tanks. The pressure switch stops the compressor through our code when the air pressure is 120 psi in the pneumatic tanks. Pressure gauge shows the pressure in the tank. We can empty the air in the tank manually thanks to the pressure vent plug. The pressure gauge lowers the air that comes from the tank to 60 psi. Double solenoid valves can place the 60 psi air in two different chambers of cylinder pistons through our code.
We used 9 motors in total, including 6 sim motors, 2 redline motors, and a snowblower motor. We used Vickers SPX model as the motor driver. We used a Microsoft LiveCam HD 3000 camera for the convenience of the driver. We used a Rev Robotics Color Sensor V3 for the robot to move autonomously. We preferred the CAN bus method for communications, for software conveniences.